one of the last talks of the day. Welcome. Everybody can read New Developments in Acoustic Simulation. Reflections on Year 1 in an Acoustic Lab. You'll hear what that is. I'm John Stork, founder of WSDG. This is an honor. Basically, I'm just introducing 3 people. But these are really 3 special people in my life. Renato Cipriano and Dirk Noy and Peter D'Antonio. Renato and Dirk were students of mine years ago, 20 plus, became interns, became employees, became partners. I was their teacher, now they're my teacher. These are 2 of the smartest students to ever come out of Full Sail, both very serious acousticians and designers. Renato's a Grammy Award winner. Dirk is a lecturer, physics professor. And they're both close and dear friends, and they're now my business partners in WSDG. And we've worked on hundreds and hundreds of projects together, actually thousands. Peter is also a very special friend of mine. He needs no introduction, of course. RPG is his invention. Literally changed the course of how our industry thinks about diffusion. And it's an honor to have known him almost from day 1 of that adventure. And is now Director of Research at WSDG. And what you're going to hear is one piece of an adventure that, as a company, we've been on. It's going to go through a few journeys here. A little basic tutorial from Dirk, a little application on how we use some of this oralization and prediction knowledge in our design work, and then a little bit of a peek into some future research that we have started on our own, and that'll come from Peter. This is pretty special for me. I hope you're going to enjoy this. So, Dirk is going to start. Thank you.
Thank you very much, John. Welcome also from my end. John gave you the rundown of today's session. It's going to take about an hour. We're going to start with Peter. We're going to end with Peter, actually. We'll start with myself, and in the middle we have Renato giving his contribution. So what we're going to do, I'm going to quickly talk about some basic simulation techniques, what it was historically, what it is today, and how we apply that know-how in our acoustic lab throughout the world. We have 3 locations for those labs. Then Renato, as John has already lined out, will demonstrate how we use the findings from the lab, from the simulations in actual architectural design, how that implies the real built world. And then, as John has mentioned, Peter will tell us something about yet another acronym in Peter's lives and our lives, NIRO, which is we'll explain later. Okay, so basics of simulation. Some people may recognize this beautiful concert hall from the outside. This is the Elbphilharmonie in Hamburg, Germany. And when a project like this is built, still up to these days, we often employ physical models to do this. This means like building an actual scale model, scale 1 to 10 or something, of the space out of plywood and whatever materials we choose to use, having these little persons out of fabric and that hopefully represent the exact absorption values of a real person in a little model. And there are sources and there are receivers displayed here. You see a little omnidirectional speaker on the left side, for example. That is as big as an egg, approximately. Made with is a handmade device. You cannot really buy that. We made this in Berlin, in the office. It's made from drivers that are usually used for headphones. And the middle picture shows you that for the high frequencies we use that little omnidirectional thing. For the low frequencies it's actually a magnetostatic loudspeaker on the lower part there, the silver aluminum foil that you see. And on the right side you see a little guy there, that's a little head, and on the bottom you can put a microphone inside, 2 microphones inside, and the channel from the ear actually connects to the microphone, so you can record in that little model that you made. You can actually put a little listener in the listener position. This is a traditionally, historically spoken This was the first type of simulation that was used in the world. Started about 100 years ago, still being done today. On the other hand, what we use mostly today, because not all the projects allow physical models, we use mathematical models. Mathematical models are basically, we enter geometry into a computer using different tools, either AutoCAD, SketchUp, Point, Matrix type of build-up. Then we dress that up with some acoustical properties, absorption values, diffusion values, what we know about the materials that are being used in that space. And those tools can also be used for some visual checks, like visibility, lines of visibility, things like that, at the same time as we do acoustic studies. How do these models work? It's very roughly, you see here the source, which is the loudspeaker, for example, an instrument. You see the receiver, that's us, or a measurement microphone, our ears, for example, or a measurement microphone. You see a surface there, could be the wall or the ceiling. And the first thing that happens time-wise is that the sound from the source goes to the receiver. It's a direct sound. You always have, like you listen to one of those two speakers in this room, and you have a direct path to your ear. However, if you have that reflecting surface, the source is never really kind of getting out to sound like a laser beam. We have some sideways projection, and it's going to be doing this. The question is, in the simulation programs, where is that reflection point really happening? Where do we have the reflection point? If I speak to somebody in the back row, for example, we take, not the loudspeaker, but my voice, there's a reflection point somewhere there in the floor, but where exactly is that? The simulation program creates this mirror source, you see that, mirrored on the surface that we actually want to look at, and connects the mirror source to the receiver. And the point where the mirror source actually penetrates the plane of reflection, that particular point, mathematically very simple, is that to be calculated, that particular point is the reflection point. So if you look at that in a time diagram, we have the direct sound that comes first to the listener, then we have a little bit of nothing, because nothing happens, and then the reflected sound arrives at the listener position. This graph that you see on the right side, the blue and the purple, that's a very simple impulse response of a very simple, simplified situation here shown to the left. In reality, we have many, many more surfaces. We have rarely, maybe in the desert, we have one surface, and that's an absorptive surface, not a bad example. But in most cases, we have ceilings, walls, floors, we have furniture, we have other pieces of reflectors in spaces. So there are a lot of more energy peaks happening in a real impulse response. We'll get to that in a second. One major question in the models is that blue circle that you see there, that blue little dot, where the reflected sound hits the wall. What happens there is defined in the model by absorption factors, diffusion, and other parameters, and that means that maybe the energy leaving the surface is less or different than what came in to the surface. In a more complicated way, we are now, the graph before, we were looking at first order reflections, that's just one reflection point from every source. If you look at multiple reflection points, we have a path, for example, from this is the source here. You see my cursor? No, you don't see my cursor. Let's put it this way. Like this. This is the source, and there's direct sound, of course, and there's also the one reflection, the first order reflection, but there's also second order reflection going over both the surfaces. And to get to that reflection, you have to construct more mirror sources than before. There's even more complicated reflection paths right here, like this. There's also energy coming to the receiver from the source. In simulation tools, it's really, for a big part, keeping track of all these data points that are being found in the calculation. It's a very heavily administrative task for the program to keep track of which path goes where and is it important or not. The criteria, whether it's important or not, can be defined in most programs as like a circle, a sphere around the listener. Whatever happens in a certain sphere, you can define the size in most programs, in that particular sphere is important. What's outside the sphere, we can forget about because we're not going to listen, we're not going to hear it. It's outside the scope of observation for this particular task. And sometimes you see that here, I mentioned that here cone tracing, pyramid tracing mean that we don't have rays being simulated, but we have cones being simulated in a space. Let's get to some more of this. We are seeing now one single impulse that I'm producing here, travels through the air, comes to your ear as one blue line, and then there's nothing else coming. We take that impulse, it's a very simple impulse response, a dry impulse response, and we use the acoustical model to calculate the proper impulse response of that space that we simulate, that theater, for example, that's displayed here. We result in something like that. We have the direct sound, still the same, but we add more reflections because we have so many surfaces in that model from all the surfaces I mentioned before. So it's a complex array of lines that show, every single line shows a reflection from a particular surface. Like this is a graph from the real simulation program. You see very quickly you have dozens, if not hundreds, of those reflection points in such a graph. We can, in the simulation programs, we can determine where they come from. Are they from the sidewalls? Are they from the ceiling? It's important to understand the characteristics of the sound in the space. Anyway, we are staying with that impulse response that we have received we have gotten as a result from the simulations, and we do the following now. We take an anechoic recording. This picture I found on the internet. It's a guy singing in an anechoic room, which is a reflectionless room. We have only the dry sound from the singer or the instrument on the recording, and that anechoic recording is being convoluted. You say it's kind of you multiply mathematically with the impulse response of the particular room that you're looking at. So we add to the singing that is being done in the anechoic room, we add whatever reflections the model gives us that have to be added correctly. And then with that impulse response we can transfer that signal to our acoustic lab. We could obviously also transfer that to headphones, for example, or loudspeakers, but I'm going to explain a little more about the acoustic lab in the next couple of slides. So we are, for now, taking the impulse response, having an audible file, the anechoic recording, convolute that with the impulse response of the space. That means basically adding the reverb of the space, that is really the reverb of the simulated space, and we're going to listen to that in the acoustic lab. The acoustic lab uses the simulated file, and also not just in a simple way, not just in a stereo way, but in a multi-channel way. In the simulation program you can select multiple formats how the acoustic signal is being generated, and what we use here for the acoustic lab simulation is this 5-channel, which is 5 microphone channels in Cat Acoustic, for example. You see that here? You can actually, with one impulse or one anechoic recording of a voice or an instrument, we can create 5 independent audio files that are convoluted with the correct impulse response at a particular microphone position in this 5.0 configuration. So we do that at a particular location. We select the listener location, and we do that once in the bass plane at 1.2 meter ear height, which is the sitting person, whatever that person hears from 5 different directions. So it's kind of the bass plane, if you want to say that. And we do that the second time. We move the listener position up about 2 meter, and we have a second plane of simulation to create another set of 4 impulse responses. So you see it now, we're kind of stacking impulse responses. We had 5 at the bottom for all those 5 microphone positions, plus we have 4 at the top, which is the height layer of the acoustic lab. So we have from one impulse or one anechoic file, we have a resulting 9 separate audio files that represent the original signal convoluted with the 9 impulse responses generated in the model at those particular positions. So what can we do? If you see the same theater here, you see the source, it's a piano here on the stage, you see our listener here, this is a little office chair sitting here, and what we do now, is you see the reflection paths in blue, and we built a little room around this. And now we kind of forget the hall, we're just in the room, and the loudspeakers do generate the reflection paths for us. So there's no hall really present, but it appears to the listener as if the hall would be present acoustically. So this is really quite fascinating if you sit there. This is the room in Switzerland, in Basel. You see those 5 channels at the bottom and the 4 channels in the ceiling. And we also augment that with VR goggle, so people can sit in the chair and they can have the goggle and they can look at an architectural model, 3D representation. They can look around and the sound field will stay stable. And if you think about it, that is like reality, because in reality you sit in a space like here in the concert hall, and I am constantly here. The source is always in the same position. Even if you choose to look at that wall, you'll still hear me from this direction. With headphones it will not correctly represent the location, because you would turn with it, unless you have a head tracker, but that's much more complicated. So this is really simulating the 3D sound field. Oh, there's exciting on the other side. And you can stand in a train station and you can look at the train and you can turn your head and the sound field of the train stays where it was originally, because the sound field is outside of your movement. It's in the room and the loudspeakers don't move. So this is second room we have in Berlin. This is for the specialists. This is Masonic Room. The other one is Oro 3D Room. This is Ambisonics. Slightly different formats. This is instead of 5 microphones spread out over like a geometry field, like a real dimension, we have multi-channel in one location, and we have no less difference in the signals from the travel time through air, because it's all going to one location. Ambisonics is one location recording. And this is the room. I'm missing the 4 ceiling speakers here on this picture. This is a lab we have in New York. This is a view of the software. We use Samplitude as a replayer. And this has a really nice touch, because we can have those 9 audio files that you see here on the waveforms, and we can convolute them in real time with a reverb processor that is custom to each channel. So the reverb processor, kind of you see that here, is using an impulse response. Every track uses its own specific individual impulse response that was generated in the model by the mechanism I tried to explain with the 5 microphones. So that allows us to actually play a file that was created, for example, an announcement in a train station. And you can pause the file and you will hear the room reverberating as if somebody would really speak in that room. You still hear the reverb because it's generated in real time. The processor, like a normal workstation, can generate 9 channels of reverb with no problem with real room simulation algorithms. So this is really, really neat. Okay, this concludes the first part of our presentation. I'm going to hand this over to Renato, which is we're going to continue on some applications of this.
Okay, so let's take a quick look at 2 very different examples, both in their architecture and their acoustics. It would have been much harder to design if it wasn't for some simulation tools that we need to use. First one, this is a very interesting church. The last design by the Brazilian architect Oscar Niemeyer before he passed away. And we got hired to do the acoustics and the sound systems for this facility. It's a very large construction. We did some studies for the impact noise for the external area where we have the stage over here. This place is in construction, but the most interesting part is the internal room acoustics for the church. What you see as a blue line is a glass wall. It's about 15 feet tall. Interesting from an architectural point of view, but not very interesting from an acoustical point of view. You can see here, this is the first simulation we did, showing 8 seconds of reverberation at the low frequencies, and about, from 5 to 6 seconds at the mid-range. The dotted lines are the limits that we're working with, and they are high. It's still high, 2.5 to 3 seconds, because we have a pipe organ in the church. So we're going to need a mix of acoustics and electroacoustics to solve this project. So we're going to do, well, the first thing we thought of was to treat all the ceiling with different treatments, and this is what we presented to the architect. We had a space here underneath those slabs, those green lines that we could also use to add some absorption in the room. And we also suggested to get some angles in those side walls, so we could aim reflections to the audience where we can get some absorption. From these 3 ideas, only the green was accepted by the architect. Until we had a meeting to show them an oralization of this space. And we were lucky enough to use as the oralization source a recording from this TV program that the bishop from this church, who is actually the owner of the project, he let us use his voice. It was a recording from the TV, which is quite dry. As Dirk mentioned, for oralization we usually go with anechoic recordings, but this one was dry enough, and because it was his own voice, it was a great example. Just a quick reminder, this headphone here just reminds us that the way we listen to oralizations is using headphones. But here, of course, is just an illustration for you. So let's listen to the original file.
Auxiliares de Nossa Senhora da Piedade, que aqui servem, com tantos voluntários, evangelizadores e colaboradores.
Sorry for the Portuguese, but this is just to give you an idea. And then we got this file and we played inside of the model with the original architectural design that we couldn't change.
E colaboradores
It didn't take too long for that meeting for them to, accept whatever we wanted to do. So the drawing on the left shows some ideas for treatments at the ceiling area. The colors represent different types of treatments. Each color, this is a drawing extracted from the CAT Acoustic software. On the right side, you see an electroacoustic solution, which is this very thin column, about 15 feet high, very directional, DSP controlled. And at the top, you see the histogram of intelligibility, which is around 0.6 for the most part. Here you see the intelligibility distribution at the audience area. This drawing shows the reflected ceiling plan with the treatment ideas that we had. And just one thing the architect asked us for was to have all of this to look as one single element. So we use that perforated board to hide all the treatments. So what we get acoustically is a combination of those perforations and whatever we put behind them. And here we can listen to 2 solutions for the PA. One of them, which is version A, would be 2 of these columns that you see here on the right, one on each side of the room.
E colaboradores aqui sempre à disposição dos peregrinos e visitantes.
You can hear a little bit of the reverberation of the room because we're using 2 columns. So now we're going to listen to just 1 column.
E colaboradores aqui sempre à disposição dos peregrinos e visitantes.
You can hear that it doesn't excite the room as much as the other options, so this is what we're going to go with. And we can still have natural sound for the organ. because we're going with 2.5 to 3 seconds in the room. You might want to turn it down just a little bit. The project is still in construction. We expect it to be done next year, so we're very excited to go back there and make some measurement and compare to these simulations that we did, which is something we could do for this project in China. This is the most prestigious conservatory of music in the city of Hangzhou, and it's a very large recording studio with a big live room, about 3,000 square feet, and 2 small booths. Here you can see some architectural ideas in place, and these softwares and these simulations too, they do allow us to play with these ideas, because we can always go back to the boards and change things before we actually build the room. Very large control room. Main speakers not in a very ideal position because of, console bounce and cancellation that you can get from that. But this was a requirement from the client, so we're going to give them what they want and do the best that we can. These are the smaller recording rooms, a piano booth and a drum booth, as they call it. This is the reverb time for the piano booth after it was done. I want to bring down the brightness in the room, just throw in some rugs and you're done. Control room, pretty large, close to 700 square feet, and it has a cutoff frequency at around 70 hertz, which means that above that frequency we have more of a statistical behavior in the room. And this was an EAST model that we did to check on the reverberation time. And here we're more concerned about the high frequencies. And the reason why is because at this moment in the project we haven't done yet what we call the low frequency analysis. So we're just paying attention to the high frequencies. After the measurements, this is an average curve from those 3 positions, right at the target that we designed for. And if we overlap those 2, you can see that they're pretty close. We had to do some adjustments in the high frequency domain. But then, after this, we had to check the low frequency content. And to do that, we used different simulation software which is called ABAC, that can show us the distribution of pressure in the room based on the speaker location and the room geometry. And you can check this for any frequency. For example, go to 47 hertz, you can see there's some pressure here, 82 hertz, some pressure in the back of the room. And now we go back to the boards and we can start designing some devices or some materials that we can put in, some types of construction methods, like for example building a platform that can work as a Helmholtz resonator for those frequencies that we could see from that model. Here at the ceiling, same thing. We have this entire area that we can work with. If you look at those pressure plots, we can easily create some kind of broadband absorber that can take care of most of that frequency range, so that we can get a very nice and even time domain waterfall display, such as this one. If we go back to that curve and extend it to the low frequency, you can see that at around 30 hertz we have 450 milliseconds, which is pretty dry for a room of this size. This is about 70 square meters, very, very large room. And this is what gives us that, tight bass response in the room. This is a comparison during the early stage of the design. we use two softwares, Acoustics and AES, and we played with both so we could learn the results, how different they were, and they actually were a little bit different from one and the other. AES was a little bit drier, I believe. And so we could adjust based on those simulations to get our final curve, which looked like this. A little bit of difference in the highs that we could adjust, and the lows, both for the good. We have a brighter room, and we have a much more controlled low frequency. This is the material I was talking about. It's just wood, small pieces of wood, and they painted it at the site. Here we have an oralization of drums. I'm going to show you the drums so we can compare to the actual recordings that we did. You can hear a little bit of, more dance in the low end compared to the final recording. It was pretty nice to be there and have the chance to record. Some of the teachers were there when I was there making some measurements, and we ended up recording some stuff. Very easy to record in large volume. Change here, hold on a second. And here just one more example, so we can listen to the room sound. Just ambient mics for the flute. Very natural sounding. Helps when we have a good player. So, very excited to see what's coming next, which is a new development from Peter. So, Peter, please.
Thank you, Renato. So what Dirk and Renato have very nicely illustrated is that you can use geometrical acoustics to design large spaces. And the assumptions that are made there, and it's amazing how well the realizations sound, the assumptions are that the phase upon reflection is neglected. And so the reflection coefficient is approximated by the use of absorption coefficients and scattering coefficients. And the lower limit is limited to what is called the shorter frequency, which is where the modal frequencies become more unified. And that's usually around, let's just say 100 hertz for talking. When you get to small rooms, you cannot ignore the phase change at the boundary. And so instead of absorption coefficients, you have to use complex impedances. And so what I'm going to show you today, literally for the first time, is a new program called the non-cubic Iterative Room Optimizer, which we acronym is NERO. And this program will simultaneously optimize the shape of a polygonal room and the locations of speakers and listeners, optimize the modal and the speaker boundary interference response, which I'll explain in a minute, using boundary element method and a genetic algorithm. Basically doing what Renato illustrated at the end with ABEC, but in an iterative way. Applying parametric pressure absorbers. This is something that I'm going to introduce in a little bit. Tuned to the frequencies that exceed the threshold, a threshold in the modal response. From a library of calculated dampers using the transfer matrix method. So this is an example of cubic room modes, which you're all familiar with. I'm not going to belabor it. Speaker boundary interference response might be new to some folks. And what happens is if you buy one speaker, how do I show you? house.
Uh,
You buy one speaker and you get four for free, such a deal. And so what happens is, at the listening position, you're hearing the coherent summation of all of those 5 loudspeakers. And what happens is that generates a notch which you cannot equalize. And if you have 1 boundary, 2 boundaries, 3 boundaries, it's pretty steep. It gets steeper. And then if you move the speaker closer to the trihedral corner, the notch moves to higher frequency, which you can control with porous absorption. This was the basis of reflection-free zone design that we talked about 3 decades ago. So around 1997, we developed an iterative solution to these small rooms, but in a cuboid room. It's a room with all 90-degree corners. And so you start out with a design, you calculate using the image model, what is used in EES and CAD Acoustics, and you generate both the modal response and the SBIR. And then you take and you calculate both of their standard deviations using this formula, and you weight the 2 standard deviations, depending upon which you want to stress more. And if it's okay, it's fine. If it isn't, you go into a genetic algorithm which looks at hundreds and hundreds of iterations. And that's what's going to be new. And so now, after 20 some odd years, we're looking at real rooms, rooms that are polygonal, they're non-cuboid. And so in this case, we're not just going to optimize the length, the width, and the height. We're going to optimize the actual coordinates of all of these vertices, in addition to the positions of the loudspeakers and the listener. It's a much more challenging task. And so what happens is, from these vertices, you generate planes, you connect all these planes, and we're using a program called Gmesh, in which you basically mesh the planes with these little boundary elements that are the size of about 1/8 of the maximum, the wavelength of the maximum frequency. And then you generate what is called a fitness metric. That's the combination between the weighted impulse, the weighted standard deviations of the modal response and the SBIR. And so here you see the modal response, I think, can you see it? And down here you see the SBIR. And so the goal here is you have these various inputs, as you can read, and I'll just describe that visually in a minute. And you get a certain number of outputs. You get the frequency response, the impulse response, and the SBIR. You weight them to determine the fitness metric. And then the program, you go into a genetic algorithm which iterates hundreds of times until you obtain the best fitness metric, which is shown here. This is, of course, as if the world was perfect. Both of them would have a 0 standard deviation. And you do the best you can. So let's see how you would apply this in a real room. This is a case study in a room in which we could vary everything. We could vary the positions of the vertices, the positions of the loudspeakers, the positions of the listeners. And so this is an animated GIF that Sam Kramer, who's here, created. You basically input the positions of the vertices. You then select the receiver location or receiver locations. You can have as many as you like. You then set the number of listeners and their locations. Then you move over into a constraint area. You could also have dependent sources. And you move into the constraint area where you define how many iterations you want to have in the genetic algorithm, your frequency response. And then what you're going to define next is the volume around each variable. So this is a volume in which the vertices can move, a volume in which the speaker can move, in which the listener can move. And once you do that, you then set the maximum and minimum distance between the speakers and the listener, and then the angle between the speakers and the listener, for a stereo situation. And you then determine the weighting between the SBIR and the modal response. And we'll then show, what we're going to show on the next slide is the actual program in action. And And they say beauty is in the eye of the beholder. Well, to these eyes, this next slide is beauty, because I've been waiting to see this for 2 decades. So here what you see is the spectra basically moving. Every iteration through the genetic algorithm, up to hundreds of iterations, you see the spectra changing, you see the vertices, the speakers, the listeners, both in plan and section, and you see the fitness metric decreasing. So it went from there to there. I think it'll move one more time. And when it moves to a value which you're striving to achieve, it's the end of the optimization. So now, this is sort of what you can achieve. This is where you start. This is the spectrum where you start. At the 60th iteration, you've got it to this point. At the 114th iteration, you see that we really dramatically flattened out the modal response. So what we're going to do now is look at another case study in which we don't have those options. So this is a case study in which the room is built. We can't vary the shape of the room. In fact, we couldn't even vary the location of the speakers and the listener by very much. So the room was not quite cuboid. So we ran the optimization in Nero to get the frequency response. And then you see we have problems here and here. And so we apply a damper. Now, this is a little different than, buying the bass trap and putting it in the room. These are very precision dampers in that we have generated a library using what is called the transfer matrix method. All that means is that we can define, in a parametric sense, you're familiar with a parametric equalizer, we can define the center frequency, the bandwidth, the maximum absorption, and we can also determine how much surface area we want to cover with this absorber, this damper, put it anywhere in the room. So this is for a membrane absorber. I've used modified the transfer matrix from my book and also from Rob Oldfield's PhD thesis. And we've also done that for Helmholtz resonators. But I have to tell you, in 1 or 2 years, all of these conventional designs will be completely surpassed by metamaterials, which we're also working on. So you see here, this is the complex impedance. This is the admittance, which is the reciprocal of the impedance. And then this is the absorption coefficient, which is determined from the impedance values. So we're going to be calling this an acoustical parametric equalizer. And we're going to call this an APEC. So you're going to be hearing the word APEC as opposed to an EPEC. So an APEC basically modifies the acoustic fields in the room so that you can hear the direct sound. An EPEC modifies the direct sound to compensate for acoustical problems in the room. So we want to do whatever you are able to do with electronic parametric equalization with acoustical parametric equalization. And so we have a damper module. We're going to run through what this damper module is. So now that we know what the problematic frequencies are, we're going to go down here and we're going to select them. There was a problem at 37, another problem at 71, another problem at 100 hertz. So we've selected them and the resolution. What we're going to do now is to define 3 planes where we're going to actually calculate the pressure plots. The way Rinaldi showed you in 3 dimensions, we're going to show you these 3 pressure plots. So we're going to see the floor plan, we're going to see the back wall, and keeping in mind that dihedral and trihedral corners have the highest pressure in the room, and that's where you want to put your damper if you can, if the architecture allows it. So now this is just inserting the admittance of the 3 dampers that we utilized, one at 37, one at 71, there's another one at 100. And then you'll see the combined illustration of all of the damper admittances. Being illustrated here in this box here. Now this basically illustrates where we place the dampers. Notice we place them in the back of the wall at the high pressure locations. They can be placed anywhere in the room. But it's important to look at those pressure plots to see where the most effective way is. And so this is what we've accomplished by putting the dampers in. Now look at this dip at 55 hertz. The reason that dip was there, I'm just going to pause this for a minute. was because and that was intentional, the bandwidth of the two dampers was too wide. So they overlap, causing a dip in the response. This is why I'm trying to stress the fact that we don't just want to put a broadband equalizer in the room, we want to put a damper in the room exactly at the frequency we need to correct, with the bandwidth that we need, at the peak frequency we need, and with the surface area that we need. And so this is the resultant, okay, that was the dip that I was alluding to. Now, just to illustrate the fact that you can put a damper in at the wrong frequency. And this is what would happen if you put a damper in at 55 hertz or so, where you don't need it. You basically make the matters worse. So it isn't a question of just buying a bass trap, putting it in the room. It's putting in a precision acoustical parametric equalizer. So then we can also then show the decay of the modes, which is very important, which Renato, I have two people that I work with, Rinaldi and Renato. They're both in Brazil. So here you see the decay of these two problematic modes, and with the application of the dampers in exactly the right location, at the right bandwidth, at the right peak frequency, and the right surface area, we've completely annihilated those modes. But the important point that Renato alluded to in one of his slides is that you want to basically match the decay time in the low modal response to what it is in the midband, so that you have a really tight low end. So when that bass drum hits, it just hits and doesn't ring. So what to do? Obviously, there's always things to do. We want to accelerate this BEM genetic algorithm iteration using parallel processing. We're using a Python code. We also want to determine accurate values for the complex impedance of the boundary and the complex impedance or admittance of the dampers. Now, you can't go to the back of a book and you can find absorption coefficients. They're ubiquitous, and most of them are wrong. But you can really never find complex impedances or admittances. So we're going to be creating a whole library of complex admittances using a very special device of mine, which is a 24-foot long, 7-ton steel and concrete impedance tube. It's 2 feet by 2 feet. And from this measurement, we can calculate the complex admittance and the absorption coefficient, which just comes from the complex admittance. And so I just wanted to thank Rinaldi, Petroli, and Sam Kramer again, whose incredible programming made this all possible. And so we will continue, and so I want to thank you all.
Thank you very much. I see that we have a couple of minutes left for some questions. If there are some questions or comments to the topics that we presented.
What's the prediction and certainty you expect from this new model? Normally it's like up to 20%, right?
Precision.
Yeah.
Yep.
And with improvement, yeah.
Oh, 100%.
Thank you.
So basically, to answer that question, without being silly, what WSDG built was a test room. It was in a basement. It was a storage area. We call it the Acoustic cave because it's a cave. And so it was built to basically give us a test bed. So the room, the way it was designed, has a mode at 45 hertz. Very pronounced. We deliberately misdesigned this room to have that mode. So now we already know how many dB of reduction you get per square meter of surface area. And we're going to test it in that room. So, like I said, I've never mentioned this program to anybody, so we really don't know its accuracy. But the theory has been used for years. The theory is solid. The boundary element theory is solid. The genetic algorithm is solid. What is unknown are the input variables of complex admittance. That's why we have to really measure those and build a library of that. We have a library of designs in the room, in the program, of building preliminary designs that we can go to. We'll have a level of things to go to. And so we're trying to get it to, we'll never get to hands-free AI, but where we're at now is sort of assisted AI in the sense that you have to put some variables in, and from then on, the program is basically doing all the thinking. You put some more variables in for a damper, and the program does all the thinking again. So, thank you.
Also, standard construction materials like gypsum walls, we don't have the values for that either. So we need to measure them also to get to those values. Yes, please.
In multivariable analysis, when you're optimizing things using some minimization algorithm, often in a n-dimensional vector space, you have these minima. They're somewhat periodic because that's our nature of our business. How do you know when you're in an absolute minima?
Right.
And over here, there might be a deeper minima that you might want to get to, but how do you detect that?
That's a very good question. So there are many types of multidimensional optimization techniques. We used to originally use a downhill simplex approach. Downhill simplex simply means, let's say you're in a mountain range and you want to find the lowest valley. So you walk down the mountain, you get into the valley, you have a cup of coffee and say, I got to go back up the mountain to look, see if I can get into a lower valley. And those are called the lowest energy level. So the only thing you can do in that case is you come to what could be a false minimum, and then you basically, from that position, you basically introduce random starting point again. And you repeat that over and over again until you keep coming to the same low energy point. In the genetic algorithm, that happens just automatically. Genetic algorithm is really is an amazing iterative tool. It basically follows Darwinian survival of the fittest. You start with a population of parents. Each of those parents has a set of chromosomes that have genes in them. The genes basically are the variables. So to make a long story short, those parents, they're promiscuous. There's no marriage vows or anything. They can mate with anybody they want. And they provide offspring. And then you evaluate those offspring. And then you introduce a mutation because otherwise you're going to have inbreeding. And so a mutation introduces a whole another possibility. And you just keep iterating that until your fitness metric satisfies your idea.
And that's in your current software?
Pardon?
That's in your current software?
Yes. Wes?
Yes, couple of quick questions. One is, I guess, simple, yes or no. Can you put the speakers all the way back inside the walls?
Yes.
Yeah.
Okay, great. And the other question is, you're talking about being able to specifically figure out exactly how many, say, square meters of, let's say, a membrane trap to tune, let's say, ringing in a room. I'm just trying to figure out on a conceptual level how much sense that makes, because if a frequency is ringing for a modal situation, don't you really want to throw the kitchen sink at that? And I mean, any ringing that's left would be wrong. So how is it possible to absorb too much? You can't absorb the actual direct sound with a bass trap, as we know.
Yeah.
So what's the concept in figuring out exact square meters in that?
If you introduce absorption in a room at the wrong frequency, you're just going to...
Oh, no, I mean, let's say you have the frequency, but you're trying to figure out how many square meters now. Should I do the entire wall or half the wall?
No, I understand. Yeah, I've been trying to... I think the industry has been trying to answer that question for decades. And we finally have figured it out now. So we have a plot of dB reduction per square meter. So if you've got a peak, that's 60 dB above the mean, you can just determine how many square feet of absorption you have to use. That's why it's important to use a parametric, because the area that you use also depends on what the absorption coefficient is. Many of the conventional absorbers that we've been using for years, they never really get up to 1, but the metamaterials will. And actually, these new designs that I have can actually get up to 1. So, knowing what the peak absorption is, you do it by trial and error. To be honest, that's not optimized. That's not part of the genetic algorithm.
Got it. Okay.
That can be done. Once we're doing the experiment, we're looking at a lot of different types of peaks and applying by trial and error this much absorption, that much absorption, this much absorption, and coming up with this design curve. So if you've got a peak that's 6 dB above the average, you know exactly how much area to include at what the maximum absorption coefficient of the base of the absorber is.
Well, in answer to what, in reality, it might not, it may be how much you're actually trying to get. Okay, because in reality, this program has really been, this work that we're doing is really about small rooms. This is basically for our control room design. These rooms are small. And as Peter pointed out, they're also real rooms. So that means they have doors and windows and surfaces that you can't touch. Building code issues. There's a lot of other things going on besides just a sort of theoretical square, which Peter did the seminal work on that years ago, and that's what's plagued us. Okay? Almost none of our rooms are rectangular for other reasons. Some aesthetic, but some acoustical. Usually first order reflections out of a loudspeaker. That's the first reason why you might not have a rectangular room. So in answer to your question, Wes, it's really more, can we get at least a minimum amount somewhere? That's usually what we're struggling with, as opposed to, well, we'll just throw the kitchen sink at it. And we're lucky if we get 1/10 of a sink sometimes. Okay, so this is to tackle real world stuff.
Yeah. That's exactly right. So, as Dirk mentioned, we don't even know what the complex impedance of drywall is.
You gotta find out though.
But you're working on that. We're going to.
We're going to find out.
We're going to find out.
One of these rooms has it has mirrors, it has windows all around. What do you put into the program?
They had on that misdesigned room. This was a storage room in our office that took months to empty out, and it just happens to be at 45 hertz. I mean, it wasn't like we did, okay, now we'll work backwards. We had the room, and then what we did was we made it very, very stiff. We've just put so many layers in the room that it's basically stiff. Some of it was concrete anyway.
The nice thing about these types of rooms, these small rooms, is that typically the wall sections are massive. And in that case, the value of the complex admittance is pretty much 0. So you can actually use the real part of the admittance, but you still have to know what it is. But as you get into rooms that might not, let's a control room window. That window,
or residential construction.
Or residential
home
construction,
theater,
or a home theater, or where a lot of sound's going right through the wall. You've got to know how pliant this boundary is. So there's a lot of experimental work to do. And fortunately, I have this impedance theory, which I've had for I don't know how many years, 25 years. We moved it from RPG's original location to its new location. I can't believe we did that. But it's a 7-ton steel and concrete box.
Shape of an object are you using? And is placement extremely important? Would you place it, for example, in the maximum spot where that mode is most high pressure, like the antinode, for example?
Okay, so most of the low-frequency absorbers, despite what you read about in the audio magazines, where people are putting foam in the corner, porous absorbers absorb where the particle velocity is the maximum. Pressure absorbers absorb where the pressure is the maximum. So the maximum pressure locations in a room are at dihedral corners and trihedral corners. So that's where you want to start. And then, if there's an architecture, as John was mentioning, you can't do that, well, then you look at these pressure plots and you see, where's a possible other location, because you could put a ton of pressure absorbers in a room at a low pressure location and you accomplish nothing.
Nothing will happen. Yeah.
So you want to start at the really, really high pressure locations. And I think your other question was, what do these absorbers look like?
Yeah.
They're just basically what we've been using for years. They're membrane absorbers and Helmholtz resonators. But most of the
One more minute.
okay, most of the membrane absorbers are limp masses, and they vibrate this way. You can't really calculate the performance of that because you don't know what the constraining force is on the ends. So I'm actually designing a different type of membrane absorber for the Acoustic, in which we think of a subwoofer. Okay, so take the speaker out and throw it away, and attach an MDF panel to the surround. And now you have a piston, so you don't have this type of motion. You have this type of motion, which can be accurately calculated with transfer matrix method. So that's going to be, we're going to be implementing that in the program. And then, like I say, pretty soon we're going to be using metamaterials, and the whole field of acoustics is going to change.
You're going to be back next year to talk about that topic, okay?
All right.